As we continue working with logarithmic functions, and we are working with the inverse function to understand that an exponential function and a logarithmic function are inverse functions or can be inverse functions. And we will have something like, along the lines of this, where we have the log base b of x equals y, or y is the exponent that we raise b to equal x. So these are the big statements that we need to understand. A logarithm, in one word, a logarithm is an exponent, and you will see a lot of the exponent rules applied as we work with logarithms. But again, log base b of x equals some number y, or y is the exponent of b, or y is the number b is raised to in order to equal x. So when we are working with these, we're going to be able to move those things around here. And then, so we have here, coming down here to a, it's asking us, what is the logarithmic form of each equation? Well, it looks like it's written currently in exponential form, so we want to get to this logarithmic form. So let's see here. We know that b to the y equals x, so it looks like in this equation, x equals 36, b equals 6, and y equals 2. So then we would know that the log of 6, x 36 equals 2. And to read that, we know that the log of base 6 of 36 equals 2. So what number is 6 raised to get to 36? 2. So this is going to be my logarithmic form. Doing the same thing here, this next example, we know that b is 2/3, y is going to be 3, right? And then x is going to be 8/27. So therefore we know that we have the log of base of 2/3 of x is 3. And then this next one, let's see here, we know that we have x is equal to 1, b is equal to 3, y is equal to 0. So we have the log of base 3 of 1 is equal to 0, and of course 3 to the 0 power is going to give me 1. So there you have it. That's writing from exponential to logarithmic form. And then if we want to evaluate this logarithm, we are looking for some value, right? We can call it y, we can call it x, some unknown. And what we can do here is we can rewrite this into exponential form. So b equals 5, I think x equals 125, and then y, we don't know. So that is going to be 5 raised to some power equals 125. Well, in order to solve this, what you want to do is remember your exponent rules, that when we're doing exponential equations, if my bases are the same, if I have a to the base of b equals a to the base of c, then since I have like bases, I know that b equals c, because my exponents have to equal if my base is equal. So what I can do is I can come over here and figure out what do I need to do to get the same base on both sides. Well, I can do 5. I know that over here on the left, I've got 5 to the y, it's an ugly y, equals 125, and then we know that 125 is the same thing as 5 to the third. So 5 to the y equals 5 to the third. So there we go. I know that then if the bases are equal, I have bases, both base 5, then I know my exponents are equal. So that is y is going to be equal to 3. So that is evaluating that logarithm. And let's see, going to this next one, we know that we have b is 4, x is 32. So if I have 4 raised to some power is going to be equal to 32. Now, these are not perfect squares of 32 to get to 32, but what we can do is use our exponent rules. We can say that 4 right here is going to be 2 squared raised to the y. 4 is 2 squared. And then what is 32 is actually going to be 2 raised to the 5th power. And if I rewrite this exponent rule right here, a power raised to a power, we just went over that not too long ago in class. We're going to have that as 2 raised to the 2y, because we multiply, and that is 2y, equals 2 to the 5th. So now I have like bases. I have base of 2, so I have the 2y is going to be equal to 5, or divide by 2, y is going to be equal to 5 halves. So there you go, evaluating that, y is going to be equal to 5 halves. And then finally, this last one, I'm going to have 64 raised to some power equals 1/32. Well, I can tell you that's going to be a fraction, and let's see where it's going to go with this. Okay, looking at that problem, we know that 64 raised to the y equals 1/32. And what I've done here is 64 is going to be 2 to the 6th power. So I end up on the left-hand side having 2 to the 6y right here. And then on the right-hand side, I know that 1/32 is actually going to turn out to be 1/2 raised to the 5th power. And using my exponent rules, I know that I can make that 1/2 into 2 by using, by moving the fraction over the bar and making it a negative exponent. And so then I know that 2 to the 6y equals 2 to the negative 5th. Therefore, I have 6y equals negative 5, divide by the coefficient, and y is going to be equal to negative 5/6. Okay, so one of the uses of logarithms is for seismic graphs and the magnitudes for earthquakes. So this example here is in December of 2004, an earthquake with a magnitude of 9.3 on the Richter scale hit off the coast of Sumatra. After the earthquake hit in March of 2005, another earthquake hit in 2005 that was 8.7. We're given this formula, and it says compares the intensity levels, where I is going to be the intensity level determined by a seismograph, and M is the magnitude on the Richter scale. So how many times more intense would the 2004 or the 2004 earthquake from the 2005 earthquake? So I've gone here and I've labeled that the M1, my first magnitude, is going to be 9.3 minus my second magnitude, which is 8.7. So then I know that the log of intensity 1 over intensity 2 is going to be equal to, let's see here, 9.3 minus 8.7. So the log of intensity 1 over intensity 2 is going to be equal to 0.6. And something we maybe haven't talked about is the base. The base of a log, if you don't see the base, it's understood to be 10. So now if I were to reorder this in exponential form, I would know that intensity 1 divided by intensity 2 is going to be 10 to the 0.6, which is approximately 4, and that is the intensity level difference. If we do the same here on this next example, registered 8.1 in 2005, again 6.8. How many times more intense was it? Well, if we have the log of intensity 1 over intensity 2 is equal to magnitude 1 minus magnitude 2, so the log of base 10 of the intensity 1, intensity 2 is going to be equal to 1.2, and then so the intensity of 1 over the intensity of 2 is going to be equal to 10 raised to the 1.2, which is going to be equal to approximately 16 times. And getting into graphing, so there you go, that's just using a word problem coming up in logs. As we worry about using these word problems, graph this function. Well, how do you graph a function? Okay, so of course to graph a function, you go ahead and plot some points and connect them with a, what I've done is I've plotted some points, put it into the graphing calculator, and now as I connect them, I know that I have an asymptote there because it never reaches 0 there. You can't find the log of 0. So then I know that some of the things here, I do know that my domain is going to be x is greater than 0 because my domain goes on forever that direction, but it does not occur at 0 because you can't find the log of 0. My range is going to be all real numbers because it goes forever upwards and downwards. Let's see here. So y-intercepts, well, considering I can never touch the y-axis, there are no y-intercepts. And then for the vertical asymptote, very important, right? Hopefully you can see here my vertical asymptote is going to be, is going to be x equals 0 because it is never going to touch 0 on your xy axis. And let's see, so if we were to look real quick, we could put that in exponential form that we would know for y is equal to x. And then if we were to graph that, it is going to end up becoming our inverse reflected over the axis of y equals x, where we talked about inverse functions before. And of course this would look something like that. There you go. And its asymptote then is the x, or I'm sorry, the x-axis. So let's see here, that's graphing a logarithm function. And looking here, it says, how do the graphs of these compare to the graph of the parent? Well, the graph of the parent in A, we're going to have the parent is going to be y equals log of base 2 to the x. The parent of B is going to be y equals log of base 2 to the x. And what we have here is, let's just think about some of the things that we know, that y is equal to a log of x minus h plus k. And we've learned in the past what these things do. H moves it left to right, k moves it up and down, and a will make it expand, or shrink or compress, expand or compress, or reflect over the x-axis. So we can go ahead and plug some of these values in and graph this fairly easy. How does the graph compare? Well, shoot, we don't even need to graph it if we know that the parent function, identifying what the parent function is, we know that a here, well, if it has y equals log of base 2 x minus 3 plus 4, well, k is equal to 4, h is equal to 3. There seems to be that a is equal to 1, so there's no growing expansion or compression. So we know that h is 3, so that it should be moved right 3 units. And then k is 4, so it is going to be moved up 4 units from the parent function. And then, of course, this other function over here, we have y equals 5 log of 2x. So a is going to be equal to 5. And then we have log of base 2 to x minus 0 plus 0. So it hasn't been shifted up or down because h is equal to 0 and k is equal to 0. So we just know that it has been stretched. That's the word I was trying to come up with, by a factor of, hopefully you know it, 5. And there you go. That's how my graphs have occurred.